All right, let's learn some more terminology associated to matrices. First, we're going to meet the identity matrix. Let's go ahead and change the color here. The identity matrix is denoted by a capital I. It is a square matrix that, when multiplied by any matrix, equals that same matrix. Think of the identity property. For addition, it would be 0 because any number plus 0 would give you that same number. For multiplication, it's just 1. Any number times 1 is the original number. So now we're looking at the identity matrix. This matrix, when multiplied with another matrix, will always equal that original matrix. So if A is an n by n matrix and I is an n by n identity matrix, then we have the following property, that A times I gives us that original matrix A. Remember, multiplication is not commutative. However, with the identity matrix, we do have the fact that I times A still equals A. So an identity matrix contains ones along the main diagonal and zeros for the remaining elements. So a 2 by 2 identity matrix would have 1 on the diagonal and 0 everywhere else. The identity matrix for a 3 by 3, again, it would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay. Now that we have identified what the identity matrix is, let's take a look at what inverses would be. So two n by n matrices, we're looking at square matrices, are inverses of each other if and only if their product in both orders, right? So in this case, if I had A times B, it's A times B and B times A, is the identity matrix. So that's how we define an inverse when it comes to matrices. So if matrix A has an inverse denoted as B, then we know that A times B must equal I. And that B times A must also equal I. In other words, they must equal the inverses. So let's take a look at a couple of examples and determine if they are inverses. So determine whether the pair of matrices are inverses. So we're going to go ahead and start off by multiplying A by B. So when we do this multiplication, as a reminder for multiplication, remember we're taking the rows times the columns. So we're going to get negative 1 times 5, which gives me a negative 5, plus 2 times 3, which gives me a 6. Then we have 3 times 5, which gives me 15, minus negative 5 times 3, which is another 15. Now we're going to end up with the top minus times the second column here. So negative 1 times 2 gives me negative 2. 2 times 1 gives me 2. And then lastly, we get 3 times 2, which is 6, and negative 5 times 1, which is 5. So notice how when we sum this up, negative 5 plus 6, that gives me 1. Negative 2 plus 2, that's a 0. Negative 15 minus 15, 0. And 6 minus 5 is 1. So that, in fact, equaled the identity. Okay, but it's not enough. We now need to check the other order. So we need to check both orders. So now we're going to do B times A. So B times A, we're multiplying the other way around. So we have 5 times this column, right? So 5 times negative 1 gives me a negative 5, plus 2 times 3 gives me a positive 6. Okay, and then we're going to now do that bottom one. So 3 times negative 1, that's going to give me a negative 3. 1 times 3 gives me a positive 3. Now we're moving on to the next column. So 5 times 2 gives me 10. 2 times negative 5 gives me negative 10. And then we're going to have 3 times 2 gives me 6. And that 1 times 5 gives me 5. We combine this, and again we get 1, 0, 0, 1. So we in fact do have an inverse because we just had it to equal the identity matrix again. All right, your turn. Take a moment, pause this video, and try the next problem. So now notice that we don't actually have to check both ways here because the moment we calculated R times S, we automatically got something that is not the identity matrix. So therefore, the answer is no. That is that these are not inverses of each other. Okay. All right, I know everyone loves fractions, so go ahead and try this one now. Are these inverses of each other? All right, so I'm hoping that the fractions did not scare you. This one actually works out pretty nicely. There are some fractions to do some arithmetic with, but we do in fact get the identity matrix for both sides of the multiplication. So these are in fact inverses of each other. So does the inverse exist? So the answer is not all matrices have an inverse. Matrix A does not have an inverse if the determinant, remember the determinant of A can be written like this, the determinant equals 0. So that's one way for us to check. So if the determinant equals 0 of a matrix, we do not have an inverse. So inverses of 2 by 2 matrices and calculating them. So if A is this matrix, then A, remember this little sign here means inverse. Recall when we saw them when we were talking about functions. Is equal to 1 over the determinant, right? That's what that equals. And then notice what happens here. Okay, notice that A and D get swapped, and C and B are now negated, so they become negative. Okay. So a couple of things for us to look at when we are finding the inverse of each matrix, right? So let's figure out if it exists. Okay, so we'd have to figure out what the determinant is. So the determinant of this matrix, called matrix A, would be 4 times 3, which is 12. Remember, now we're going to subtract the other diagonal, minus negative 6 minus 1, which is positive 6. So negative 6 times negative 1 is positive 6. So we get 6. So because that determinant is not 0, the inverse does exist. So let's calculate what the inverse is. So our A inverse here would equal 1 over the determinant. We already calculated the determinant, so it's just 1 over 6. And now we are going to take that matrix and we are going to flip A and 3. So then they get changed, and we are going to negate C and B. So this becomes positive 6 and this becomes positive 1. Okay, and so now we're going to multiply out that 1 over the determinant. So 1 over 6 times 3, that becomes 1/2. 1 over 6 times 1, that is 1/6. 1 over 6 times 6, that's just 1. And 1 over 6 times 4 is 2/3. And this is our inverse matrix. Try number 5. All right, notice for number 5 that when we calculate that determinant, we actually end up with a determinant of 0. So that's a big uh-oh. So that tells us that the inverse does not exist for that particular matrix. All right, take a moment and try the remainder of these out. I'll work one of these out. Actually, let's work number 6 out again just to give you another example of me working it out. And then I'm going to have you try the next 3 on your own. So number 6, again, we're going to start off by calculating what that determinant is going to be. 8 times 5, it's going to give me 40. And then I'm going to subtract 8 times negative 10, which gives me a negative 80. So this is going to give me a positive 120. Because the determinant doesn't equal 0, that means that the inverse does in fact exist. So now our inverse, our A inverse, is going to be 1 over 120. And then I'm going to switch 8 and 5. So I'm going to have 5 here, 8 here. Remember, and I'm going to negate the other 2, so I'm going to get negative 8, but I'm going to have a positive 10 now. Okay. And so now what we want to do is we want to multiply out that 1 over 20. So when we multiply that out, 1 over 20 times 5, that's going to give me 1 over 24. 1 over 20 times 10, that's going to give me 1 over 12. Negative 8 times 1 over 20, that's going to give me negative 1 over 15. And 8 times 1 over 20 is going to give me a positive 1 over 15. And this becomes our inverse. All right, try the next one. All right, for number 7, were you able to obtain this inverse matrix here? Hopefully you were. Okay. Let's look at the next one real quick. Let's calculate that determinant. We always want to start off by calculating the determinant. Negative 6 times negative 2, that gives me a positive 12, minus 12 times 1, which is 12. Uh-oh, we got 0. So that automatically implies that there is no inverse. Okay. All right, last but not least, try the very last one to get some final practice in before we move on. All right, and that was our last example here. So were you able to obtain this matrix here as the inverse? We're not going to go over how to calculate inverses for 3 by 3 matrix. We'll discuss how to do that when we talk about how to calculate these using a calculator. For now, by hand, you can absolutely calculate a 2 by 2 inverse matrix. All right, until next time.